Number one, in labs, we're primarily concerned about measurements. Okay? These are our quantities, our quantifiable things. Measurements have a couple different components. You have the numerical value and you have a unit. I would argue the unit actually breaks down further. Okay? The unit has a measurement unit, so a measurement component, and it has a substance component. Okay? So if I said 12 inches, what does that mean?
It's just a measure.
You don't really have a context of what that means. But if I say 12 inches for my foot, that now carries some meaning. Okay? Or 12 inches for my forearm. Okay? We have different meanings coming out of that when I include the substance that I'm actually measuring. So whenever you take a measurement, you should be including the numerical value. Most people include this. The measurement unit, most people screw this up. Okay? I will yell at you a lot for it. Okay? And the substance unit. Okay? So when we're looking at our units, you've got to make sure you've got all of those components. Okay? When it comes to measurements, we've got 4 major categories. We get distance or length. How would we measure distance or length? Touche, did not consider that. What unit would we be using to measure distance or length?
Meters.
Okay. We could get meters. I heard centimeters. Inches. Feet, kilometers, miles, yards. So there's a bunch of different units, right? So what does that mean?
Depending on what you're measuring, there's different types.
True, depending on what we're measuring. What are you going to be responsible for being able to do? Convert between each of those unit systems. Okay, so you have to have a conversion process. Okay, and that's our unit 2. Mass or weight. I use them interchangeably, just so you know. Physicists can yell at me later. Grams, pounds, kilograms. Okay, so there's a bunch of mass units. Volumes, milliliters,
Ounces.
Ounces is a fun one because you got to specify, is it fluid ounce or is it the mass ounce? Cups, quarts, gallons, Okay, time? Seconds, minutes, hours, days.
Weeks.
Okay, you get all of those kind of time units associated with them. Okay, so you're used to dealing with at least some of those. What you're going to be responsible for doing is acknowledging how to interrelate those as necessary. Okay, all of these are human inventions. Okay, this wasn't something that was defined and just brought down and now comes into existence. All of these are human inventions on how we take these measurements, which means there has to be a central standard for this. Okay? Depending on which system is kind of the core system, that standard is stored in different locations. Okay? For instance, Colorado has a standard for a lot of these different measurements, and they house it and hold on to that very, very, very tightly. Okay, under extreme security. Why might you put that under extreme lock and key? Someone comes in and changes the mass of a pound, what is that going to change? Everything. Okay? Because pounds are used in a lot of different locations. Well, now I get to weigh less. Well, maybe that gold block you've been holding on to now also changes its value because we tie it to a mass unit. Okay? So those standard units are really, really heavily guarded because if they change, everything else changes and our interpretations change with it. Okay, so there's a lot of security behind those. Most of what we do in science is based in the metric system, so that's where we're going to primarily stick. Okay, we do have to deal with the English system, and you can thank our native-born country, if you're born here, for that, because now we have to convert between metric and, for lack of a better description, the American unit system. Okay, so we have to be able to deal with those conversions. Our mass measurements we use balances for. There's a neat little YouTube link. Some guy gets super excited about the mass of a kilogram. Okay, I think it's really cool. I would recommend you take a look at it because it is really neat, but I don't want to spend any time in class. Volume. There's a bunch of different ways to do volume. Why would we invent a volume instead of just doing mass? What is different about a mass than volume?
Mass is how much matter something contains, and volume is
The amount
how
of
much
space it takes up.
True. How easy is it going to be to measure the mass of a liquid? Not as easy. Why? It has to be contained in a secondary container. Why?
Because it's not solid. It's
Liquids
properties
have
variable.
variable shapes. So we'd have to do extra things to control that phase. So we invent a new system to measure it so that it's easier to deal with. Right? That's why we have volume measurements. It's a secondary way to deal with effectively the new phase liquids. Okay? Variety of tools that you could go through and use. You've probably already used the graduated cylinder. You'll probably use, or you will use the burette in the lab. You might use the pipette, and I don't think we make you use the syringe or the volumetric flask. Why might not the syringe? Yeah, we don't trust you. Sharp-pointed objects. Okay. It's not so much a trust thing, it's a hazard thing that we don't want to deal with. Okay. So most labs don't get you exposed to syringes early on. Okay, so there's a variety of ways that you can go through and measure those. Which kind of sets up our next kind of lead-in, because those are our main categories, is how do we go through and take measurements? Okay. What is the length of that silver rod? Anything else? Just 4.2, 4.3? No one else wants to be adventurous? And 4.23? Way to just incorporate everybody's answers.
Sir, let's see, like 4.265. Okay, I was kidding.
Way to be extra adventurous. I like it.
I was joking.
Okay. The numbers in red are valid. The numbers in blue are invalid. Blue are all wrong. Officially, all of these are wrong. Why are they all wrong?
Because you guessed too many numbers.
What do you got?
It's not indicated. There's no indications. It's going by one. There's like no like.
It's only by 1 centimeter.
There is a unit specified on here. All of these are wrong because
No, you know.
we didn't specify the unit. Okay? So we all happy now to just accept that Mike entirely screwed that up. They should all say centimeter next to them. Yes. And now we're going to use our imagination and say they all have centimeter written next to them. Now the red ones are correct, the blue ones are wrong. Why are the red ones correct and the blue ones wrong? Significant figures. Okay? Sort of indirectly. Right now, what this is looking at the measurement and holding the value of what that measurement is. The ones in red have correctly taken a measurement. The ones in blue are incorrect. When we take a look at that rod, notice everybody said 4. Right? So those are not guesses. Okay? The way I've been calling these, at least this semester, is those would be truths. Okay? That is an absolute value. It is definitely 4 in the ones place. What about the next decimal? Okay? Notice that all of our measurements, it's changed. Not everybody is guessing the exact same value. It's changed. Why is it changed?
Not specified.
You're guessing. Okay? So at the 10th place, you're now taking a guess. Okay? Why do we know we're taking a guess? there's no indication between 4 and 5 of what smaller measurements might be. So you're really just guessing somewhere in between there. You're able to approximate and say that's probably about halfway. So that dotted line, or where that silver rod is a little bit less than that. So we're eyeballing it at 4.2. Okay? Usually someone comes in and says, well, it's 4.25. Okay? What you've done by adding that 5 is added an extra decimal. Okay? In this case, the 3 and the 6 over in these numbers. Okay? That information is based on the information in front. Just like with our guess. The 2 is based on the information of the 4. Okay? What could you tell me about the 4? It was the truth. You're guessing on the truth. This is an educated guess. Okay? If we move to the blue ones, our 3 and our 6, what are we basing our guess on?
The 4.2.
A guess. Okay? So you are guessing on a guess. How accurate is that going to be? Not very accurate. Okay? Which means you're making numbers up. The more numbers we throw in after here, the more you're guessing on a guess. Okay? You're saying we have meaning when we don't know anything about it. So when we go through to take a measurement, we have to report all of the truths, all of the absolutes that nobody is going to get wrong, and then we have to guess one more. Okay? And we guess one more because there's meaning there. We can draw meaning from that. Because if we look at that rod, if we just said it was 4, is that true?
No.
It is a little bit larger than the 4. It's not a 5. But by writing 4, I haven't specified that information. I haven't provided that value. Because I know it is a little bit larger, I can now add that extra place, and I've now provided a guess. So all the truths, one guess. Okay? That gives me more meaning behind the measurements, and it allows me to appropriately and consistently use my measurement tools. Make sense? What if I want more truths?
You have to have more.
Or subdivision.
I need more subdivisions. I need a better tool. Okay? So we would continue to upgrade the tool, which I believe this one goes through and does. We could put in more hash marks to now put in more information. Based off of that first ruler, we could come up with our guess of 4.2 centimeters. I'll fix it this time. For the bottom one, if we go through and look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going by tenths. This is now 4.2. Those are truths. I know where it is greater than that 2 line. It's not yet reached the 3. I'm going to say that that is at 4.26. I was just being contrary, so thank you for shouting out 5 so I could kind of fight with you. Okay? That's a guess. It doesn't matter what I write down for that, as long as I put something there. Okay? And now I'm going to take a hot second to pause the video. Okay, we'll go back to the video. Now that we're back recording. Officially, you should also report an uncertainty, okay, which is precision. I know in your lab they called it accuracy. It's wrong. It's precision. We would take this ruler, for instance, and we'd give it out to 1,000 people, and we'd say, tell me what the measurement of this silver rod is. We would total everybody's measurements, and we'd see how much they varied from each other. That variance is the precision of the ruler. Okay? That is something that has to get tested for. This isn't something that you just go, oh, it's this. Okay? You actually test for it to prove what that value is, or to come up with a good approximation. So when you were in the lab, what did you do?
We did like the greater than, less than, whatever it was.
Pretty much just guessed and specified it, except for the balance. Why, for the balance, did you actually have to write a proper precision and not just guess one? The balance is expensive enough that it actually tells you how precise it is. All of your tools should tell you the precision of them. If they don't tell you the precision, it's a useless tool. Okay? So most of the tools that you guys deal with in CHM130 are sort of useless because they don't tell you the precision. Okay? Except our balances. Those are nice. So this becomes important when we look at significant digits. Because I know you've all been exposed to it in lab, you should be able to tell me the significant digits in each one of these measurements down below. So we'll go ahead and on 3, we'll start shouting out the numbers. Okay, so 1, 2, 3.
2. 1.
Well, that was fun. Right out of the gate, you were all wrong. What the heck?
First one.
Okay. What makes a digit significant? It is significant because it was reported by the measuring device. How often are you going to be expected to do a measurement in the lecture? You're not, which means you have to be able to look at a number and know the significant digits, know the numbers that came off of the measurement. Okay? So we have to be able to know what was 0 as important and what was 0 as not important. And that's ultimately the big line that differentiates significant digits. Okay? Is it really comes down to the meaning of that 0. Okay? So 1 through 9, they're always significant. Okay? So let's take a look at our zeros. Okay? The zeros are really important based on the decimal point and the decimal point alone. For those of you that didn't bother to watch the play posit, that's cool. You went through and read the lab manual, probably talked to your lab instructor, and they gave you a list of probably 5 or 6 significant digit rules. There are not 5 or 6 significant digit rules. There are 3, and arguably there's only 2, where one of them has subparts. Rule 1, 1 through 9, always significant. Rule 2, zeros. Okay? If there is no decimal point, then for the 0 to be significant, it has to be controlled by significant digits. Okay? And I really need to get in and edit the wording here because that shouldn't say numbers, that should say significant digits. In this case, we'll say sig dig. To the left and to the right. Okay, so let's take a look at the first number down here. Well, the 1 and the 2 are significant. Okay? Is the 0 significant?
Yes.
We look to the left, we look to the right. Those are significant digits, which means, yes, it is. We get 3 sig figs. What happens when we move to the next number down?
There's only 2.
1 and 2 are significant. We look to the left, that's a significant digit. We look to the right, not significant, which means the 0 is not significant, and the answer comes in as 2. Okay? If we move to the next number, it's the same number, right? 120 versus 120, and yet the answer for the next one is 3. Well, what's the difference? We've now explicitly defined a decimal point. We need a new explanation. That new explanation is that if there is a decimal point, then the 0 needs to be immediately preceded by a significant digit to be significant. So we go back down to our number. We look to the left of that 0. What do I see? A 2, which is significant, which makes that 0 significant, 3 sig figs. Yeah? What do you guys think? You think you get all the rest easy now? Okay, do all the rest. We'll give you about a minute. That was a minute. The next one is
3.
4. Okay, we'll have to come back and take a look at that. Upper right.
2.
Next one. 2. We're going to come back and look at that one anyway. Next one. Last one.
3.
Okay. So I've got 3 circled. Does anybody want me to specifically talk about any other ones, or are you okay with just those 3?
The last one.
You want the last one too? Okay. So, let's go ahead and start down here. Why does that one have 4 significant digits? So one of the things that I do like to go through and do is underline them. So 1 and 2 are significant. I see an explicit decimal point. If I have a decimal point according to the list I've got outlined up here, I'm moving to rule 3. The 0 needs to be preceded by a significant digit. Preceded to the left. What is to the left of that first 0? A significant digit, which means the 0 is significant. Let's move to the next 0. What's immediately to the left of it? A significant digit, which means also significant. There's 4 sig figs. Yes.
So once a 2 makes this 0 significant, that other 0 becomes significant because that one's sufficient significant?
Yep.
All right.
Yep. Okay. The upper right-hand one we'll ditch for the moment. Okay, so we'll look at this kind of middle one. The 1 and the 2 are significant. Okay, I do have an explicit decimal point. For the zeros to be significant, what has to be true?
It has to be a
Significant digit to the left. Is there a significant digit there?
No.
There's literally nothing written there, which means not significant. Move to the next 0, move to the left, what do we see? A non-significant digit, which means only 2 sig figs. Starting to make sense?
Yeah.
That bottom one, what is, whoa, don't underline that. The 1 and the 2, what is to the left of our first 0? Nothing. What is the left of the next 0? Nothing. What is the left of the last 0? Significant digit, which means 3 significant digits. Kind of, sort of? Okay. Last one up at the top. Everybody got that one right. Good job. I'm going to argue that number is bad. Shouldn't write a number that way. Okay? And here's why. My pen is too good. Damn it. That's a little better. What did I write?
0.12.
Okay. Let's ask Matea. What did I write? Damn it. My pen is too big.
It looks like 12.
Thank you. Somebody can appreciate this. It looks like 12. What do you mean it looks like 12?
Decimal's really small.
The decimal's really small. If you're using a pencil or pen, you punch the table or punch the paper to put that decimal point. In all likelihood, that decimal point's going to disappear from your view. When you go through to actually enter that into a calculator or manipulate it, you're going to drop the decimal point. And instead of that being 0.12, it becomes 12. That's a really big deal. Why would I ever write 012? That split second pause of why did I put a 0 in front of 12? That doesn't make any sense. Probably makes you go, oh, there's a decimal point. Let's make that a little more obvious. I'm looking at 0.12. So that 0 is what I would reference as a leading 0, and you should always include it, not for any kind of significant digit rule, but for simplifying your calculations or minimizing those calculation mistakes. That's it. Okay? Make sense? Still comes in as 2 sig figs because there's nothing to the left of that 0. We good? Cool. So this is a fun one. How many quarters do you see? 7. Lovely answer. There are 7 quarters. So here's going to be the next fun question. How many sig figs in that measurement?
Sig figs don't count as exact numbers.
Okay. So I'm hearing a lot of people shout out actually the correct answer, which I find interesting and fascinating. So cool. Okay. When we're counting things out, the error in our counting ability, at least with relatively small numbers like less than 10, I wonder why that might be an issue. Everybody laughs. So I'm not stupid. I don't count on my hands and toes. Believe it or not, the human race is pretty insanely stupid and can't deal with numbers larger than 10. You're like, that's crap. Really? What is a dozen?
12.
Why did I invent the term a dozen if I can deal with numbers larger than 10? Okay. Just 2 more numbers, and we have to invent a whole new word for the extra 2 decimal, or not even 2 decimals, 2 values. Okay? We're inherently horribly moronic, and we can't deal with numbers larger than 10. Okay? We invent systems to allow us to simplify that. Okay? So when we're dealing with counting things, we usually say we've got no error in our measurement. An exact value has infinite sig figs. This is not 1 sig fig, because if it's 1, then you're saying it is possible that I have 7.1 quarters here. No, there's 7 quarters. There's exactly 7 quarters. Okay? So we have an infinite amount of sig figs. Does this show up with other things? It doesn't have to be counting. Where's my screen? There's my screen. 1 foot equals 12 inches. How many sig figs? This is extra fun because 12 looks like
12.
how many sig figs? It would look kind of like 2, right? And 1 looks like 1 sig fig, right? How many sig figs? It's infinite. Why is that infinite? It's not even that they mean the same thing. This is a definition. It's an exact value. There are exactly 12 inches in 1 foot. We have defined that to be the truth. Because that is our definition, those have infinite sig figs. There are plenty conversions where we don't have infinite sig figs. So don't just assume because we're doing a conversion we've got enough sig figs. Right? But our conversions on definitions are usually infinite sig figs. Kind of, sort of? Good enough. Okay? So why do we care? Okay? What do you get for the answer here? So I learned math a little bit differently, so let's see if I can pull this one off. I add it from the left to right. Right? What do you mean why? Is that not true?
Yeah.
Wait,
That's true, yeah, I'm pretty good at that.
oh, I'm just like, I've never heard of someone doing that.
How'd you do that?
I'm gonna guarantee you there's something else going on here, and don't make it all political yet. Trust me, it's okay. So there we go. There it is. Is that a valid answer?
Yes?
No, it's actually inherently wrong. Everything about that, or not everything about that, but a large portion of that is inherently wrong. Okay? And you might have learned in math class that all you got to do is add them up and everything works and everything should be happy. Okay? But that calculation made a huge assumption. That assumed that that was a 0. And that was a 0. That was a 0. That was a 0. And that was a 0. And that was a 0. Because this is science and these are measurements, do I know anything about those blue zeros? No, I know nothing about them. They could be zeros. They could also be, what's as far away from 0 as you could get? 9. Okay? Just to test my addition skills, we can try and run that again. Okay, if we run this left to right, 115, 1 6 3 6 2. I just had that one memorized. That one's okay. This one comes in 115.7.
Right at the bottom of the screen.
Will you just?
God.
Don't ruin the magic. I'm horrible at math. And I built cheats into my systems. So if we look at this, if we make the assumption that they're zeros, we get 115.63362. If they were 9s, we get 115.7346. Are those numbers the same? No, they are different. Okay? Where did they differ? So the ones place was the same, or that's not the ones.
The sig fig after.
Hundreds, right?
Yep.
Tens, ones, tenths. Okay? That tenths place is where they've differed. And if we look at a measurement, that tenths place was ultimately a...
Limiting factor.
Yes, I don't like that word yet because we didn't use that word. What was that in our measurement, that last place? It was a guess. which would mean if we're looking at our math, that place we would expect to see different numbers show up because it's a guess. I don't really know anything about it. Okay? So we're guessing at the tens place. That's where we see variability, which means everything afterwards is now guessing on a guess. Okay, so arguably those should disappear from our calculation because we don't know anything about those in actuality. So let's go back to our measurements. The last number was ported out to tenths, hundredths, thousandths, hundred thousandths, 10,000s? 10,000s? Cool, there we go. So all a bunch of places. The next one was reported out to the thousandths with a stupid TH in there. And then the first number was tenths. Okay. Where did we get the variability? The tenths place. Because that's our guess place, that's where things started to change, that's where we should report things. Did our numbers at the beginning help predict that potentially? The first number only could report to the tenths place. Where did my variability show up? The tenths place. Why? Because that 3 in that first number was a guess. I'm not confident in that value. So someone went through with enough examples and noted that when we add up a bunch of numbers with varying levels of precision, that the place, the decimal value where we start to shift is all dependent on our least precise measurement. Because they made that observation, what do they then do? Instead of making you go through and test all of those calculations, they instead say, big red box, when you add and subtract values, your answer is only as precise as the least precise measurement. You don't have to do all these extra calculations. You just have to trust that somebody actually tested it and proved it. I never knew that. I actually tested it. I was like, really? Is that how it works? It's like, no way. There it is. That's why the rule is there. Okay? It's the uncertainty in all those values. We don't know information about that. So you have to know when you add and subtract, least precise place. Okay? So what happens when we go to multiplication and division? Okay? So if I asked you to measure the area of a square, how would you do it? Length times width. So we got our two numbers there. We could mash them together and we could get an answer. What is the answer? Yeah, I looked at the bottom of the screen too. It wasn't there. Okay, it comes out to 33.488 units squared. Don't stress about the units necessarily yet. That's what your calculator spits out. Are you correct? No, you're wrong. What is the correct answer?
33.5.
Okay, so we got people jumping all over 33.5. Phenomenal job. I really like the effort. That was a good, awesome job, except you're wrong. Every time we advanced the slide, what did I quickly do? I quickly erased something. If we go through and test this, remember, we need to consider the same thing that we considered with addition subtraction. What happens if we take 7.28 times 4.69? Right? And if we punch it into our calculator, what we end up getting? Stop reading. 34.1432 units. Where did our variation in numbers appear? Okay. In the tens place. That's not the tens place. The ones place. Whoever's saying stuff, stop saying stuff wrong because you're making me say it wrong. Right? It's in the, I almost said tens again. It's in the ones place. Well, but what about our numbers would allow us to see that we need to report to the ones place? Because both of those report more than to the ones. Okay, so if we're going to report our answer, we're actually going to have to report this one as 33 units squared. Okay, we can only report out to where we had that guess. And remember the 34 one, I just made up some numbers here. Okay? So I can only call this one 33 units squared, but nothing about my measurements suggests I should report to the ones place. That's because the rule that we used for addition and subtraction doesn't apply. Okay? How many sig figs in 7.28? 3. 4.6?
2.
How many sig figs in our answer?
2.
2. The rule changes. What does the rule change to?
Oh, just of the two numbers, leave out a
The lowest number of significant digits. So if we erase everything out, the result is only as precise based off of the number of significant digits. Okay? Which means when we go through and run the calculation with those numbers, we can ignore that bottom one, I can only report 2 sig figs. So I start left to right. First number is a 3, significant digit. Next number is a 3, significant digit. The rest of this, I don't know anything about. My answer becomes 33 units squared. Okay? So we have to follow these things appropriately. This is not what we're used to doing. Okay? And the reason we're not used to doing it is that if I asked you to take these measurements, you wouldn't have reported it at 4.6 units. You would have reported it as 4.60. You would have used the exact same number of sig figs in both calculations, so it would have been a moot point. Most of science uses the same numbers of sig figs in each of their measurements so that we don't have to stress about weird oddities like this. Okay? Unfortunately, this is the lecture where you're not taking any measurements, so we get to throw everything at you. Yes?
The numbers following the decimal, like it's 0.488. If it was higher than 0.5, would you then round the units to 34 units squared?
Do you mean, would it matter if I had to worry about rounding?
Yeah, so like it was 33.48.
So let's take a look at this one. Addition, subtraction. I add those two numbers up. Calculator spits out that number. What do I report to?
1.33.
I won't accept that as a number. What do I report to? You're giving me a number. I don't want a number. Give me a place. Tenths, hundredths. I can only report out to the hundredths place, so I go down to my number here, and I go to my hundredths place, 1, 2, 3. There we go. That's where I report. My answer needs to become 1.33. But what are you saying?
The number following is higher, or 5 or higher.
The numbering following that could have an effect here. Do we have to worry about rounding? Yes. Okay? The fun thing with rounding, everybody has their own frickin' rules. Okay? And it usually centers on the 5. Okay? The rule that I've stuck with, because it's at least consistent in my brain, it's not as scientifically valid. We can talk about that later if you want. If it is 5 or larger, add 1. Because that is 5 or larger, I'm going to add 1. So my answer is not 1.33, it is 1.34, which is still wrong. 1.34 grams. Okay. What happens with multiplication division? If we take a look at that new calculation, multiplication division, how do we report out?
Least sig figs.
The fewest number of sig figs. I don't care about the place anymore. How many sig figs in 7.8?
2.
How many sig figs in 4.68?
3.
My answer needs to be 2 sig figs. 3, 6. I take a look at that first insignificant digit. My answer becomes 37 units squared. Yeah?
Yeah.
The rules, you just got to follow them. Okay? These are the rules that I follow with the rounding. That's why they're up there. Okay? They are not the same rules that the textbook followed because I didn't read the textbook carefully enough. And ultimately, I if I'm really going to go there, don't care about scientific numbers enough to really stress about the nuances of how to deal with rounding. Okay? Because I don't think it's that big of a deal. And yes, that just got recorded for all of future posterity so I can get yelled at on the internet. Whoopee. Make sense? Prove it. So if we go through the top one, 3 sig figs, only that first 0 is significant. The last 2 are not significant because there's no decimal point. We have to have a significant digit to the left and to the right. For number 2, which shifts to the upper right-hand corner, all the zeros are significant because they all have a significant digit to the left of them, so you get 6 sig figs. For number 3, I saw a lot of people telling me it was 129. Okay? That is not correct. Okay? Why do you have to include the 0 and the 4?
Because for addition and subtraction, it's the decimal place, not the sig figs.
For addition and subtraction, it's based off of the least precise place. The least precise place in this case comes in at the tenths location, which means you have to report the 0, 4. Okay? When you write 129, I'll go to you, Leah.
Okay.
For 129, why did you say 129 initially?
Because there was 3 sig figs was the lowest one.
Okay? So it is super common for people to do addition, subtraction, and start to use the multiplication division rule. The multiplication division rule tends to be easier, at least in my opinion, and so almost everybody gloms onto that one and uses that all the time. Okay? That is why, typically on a test, the one you see on sig figs, addition, subtraction. Okay? And one of those answers will guaranteed match the multiplication division rule. Okay? So you've got to watch out for that. Addition, subtraction, the least precise place. In this case, you go out to the tenths, hundredths place. For 4, if we go through and punch into the calculator, your calculator should spit out this big long number, and that is of course wrong because that has too many significant digits. Because it is multiplication division, we have to go based off of the fewest number of sig figs. There's 3 sig figs in that middle one. Our answer needs to be 3 sig figs. 1, 2, 3. So 4, 5, 4, because 8 is larger. So I add 1, and this is usually when I'll get 454 meters cubed. Everybody goes, well, I don't want to include the 0 because I don't want an extra significant digit. As long as I don't include a decimal point, that 0 is not significant. Do I need a 0 there? Yes. Why? Let's just scale this out a little bit. The first one is is 4,000. If we don't include the 0, it becomes 400. Sig figs are important. That can take a $400 paycheck and make it 4,000. Okay? Don't get rid of those zeros. That 0 is acting as a placeholder. We need it there. It must not be a significant digit. How do I ensure it's not a significant digit? Don't put the decimal. Okay? Leave that blank. It's implied now. The 0 is now acting as a placeholder, not a significant digit. Okay? So just to be clear, that answer is this one. We'll go ahead and erase all the other stuff. Okay? 5, your answer comes in as 0.03 grams. Okay? Anybody notice anything kind of bizarre about that calculation?
It went from ounces to grams.
Jerks. Try again. Why did I do that? Nobody knows anything? How many sig figs in 33.12? 4. How many in that one? A lot. How many in our answer? How many in our answer? 1 sig fig. We went from having all of this information to virtually nothing. Subtraction, you will delete sig figs. Okay, it almost always happens, which is why when we deal with subtraction in our measurements, in our labs, we try to make sure that the difference is huge. Because if the difference is large, we can keep a lot of sig figs. We don't want to do subtractions or calculations that involve subtractions in lab with small numbers because we lose significant digits. Okay. Conversely, what happened with number 3? We gained sig figs. So addition, not as big a deal because we actually increase information, okay, or the amount of information. Subtraction, we can lose it. So subtraction becomes a big deal to make sure that we're subtracting large differences. Okay? And 6, when we go through, in theory I did the number calculation right, 0.454 grams per centimeter cubed. Questions about those?
No.
Okay, I do want to point out one thing with that last one. I would argue a better way to write this, 0.0454 grams over centimeter cubed. What number is showing up in front of centimeters cubed?
1.
A magic 1. This is a much better way to write it than what's written in blue. Why might we write it in blue instead of in red? Because we have a blue pen. Shh, knock it off. What do you have?
Convenience.
Convenience. What's the convenience?
The red ones takes up a lot more space.
The red one takes up more space. So we tend to avoid doing that because we don't want to take up as much space as possible. Okay? What is it? Man spread? There it is. That's the word. Man spread. You need to man spread your calculations. Okay? Your calculations need to take up as much freaking space as possible. It becomes very, very important when we move later on looking at our conversions. We want to see a numerator and denominator. I know nobody likes fractions. You better start getting used to them. Okay? They are important uses or tools to allow us to solve things. It is man spreading, right? I got that right? Yeah. If you don't get it, don't worry about it. Okay? I would argue it's a good idea to put it all on one slide. For whatever reason, I've got it animated. So if you go into the slides, slide 25, you can print that out. Those are all your Sig Fig rules. You should make sure you follow them at all times. Just because you're about to take a picture. Sorry, I forgot. I wanted to talk about this. How important is it for Sig Figs? Okay. If you're going to be an engineer there, I promise I won't move it. You can take a picture now. For real, you can put it down. Okay. It is very important if you want to be an engineer or a scientist to track Sig Figs appropriately. If you don't want to be an engineer or a scientist, it becomes a little bit less important, though still kind of relevant behind how we do measurements and calculations. Okay? So I would still encourage you to pay attention to it. There are some people, you hear it like grammar Nazis. There are Sig Fig Nazis out there. Okay? The problem that I have with that is that nobody is very consistent about appropriately applying the Sig Fig rules in every single case. Because we aren't consistent in it, if we now get hyper-focused on that in our class, what happens? You start losing focus of the content, and you're only focusing on these stupid numerical things that are a relatively minor aspect, and you lose sight of what you're actually trying to go through and solve. Okay? So when it comes to calculations in this class, I am super aware of significant digits as an issue, super aware of rounding and all these fun things as an issue. And I try my best to always match to these things as close as possible. Okay? But that is not a guarantee. So on a multiple choice test, you might see answers with slight variances. That slight variance probably has to do with some kind of Sig Fig rounding thing that you did slightly different than what I did. Okay? If you encounter it on an exam, you should use the numbers that are given to you on the exam and nowhere else. Okay? The big reference for this that's going to become important is if you take a look at, I give you a periodic table with your exam. If you look at the numbers on the periodic table and compare them to the numbers on the wall, they're not all the same. Okay? That slight change in number can be enough to completely change a calculation. Okay? I try to watch out for it, but I want you to be aware there's issues that pop up there. You will for sure see it as problems within online homework systems, if you have to deal with online homework systems in the future, or questions out of a textbook. Okay? So please be aware of that as an issue moving forward. Okay? If you encounter something, feel free to call me out on it, and I'll try and fix it and make sure I got it right. Okay? So, let's take a quick look at a chemical reaction. A little bit of a break. This is totally the wrong place for this slide, but hey, it works. Okay, because you all did a little bit of nomenclature. Let's take a look at this. Solid sodium hydride reacts. So we're going to pause right there. Solid sodium hydride. That's an awful lot of letters. I don't want to write all those letters. Help me abbreviate. Okay, I think I saw you mouth back there, Na. What is Na? Sodium. Hydride. H, not H2. We'll get to that in a second, believe it or not. I definitely didn't give myself enough space. Okay. Cl, there's no chlorine. We just said solid sodium hydride. So you gave me sodium, you gave me hydride. I said solid sodium hydride. You gave me sodium, you gave me hydride. I need the solid. I want to know that that's solid. How do I know it's a solid? I'll put the phase afterwards. This is my notation for how I build these things. Okay? Because you all did nomenclature, you should be able to tell me that sodium hydride is a correct formula. How would you do that? Counting the charges. What is the charge on sodium? A +1. What's the charge on the hydride? Admittedly, that's tricky. It is a -1. Is that formula correct?
Yes.
Yes, the charges have balanced out. The overall charge on that compound is 0. Sodium hydride, S, is fantastic. We then say reacts. What is reacts? And the fact says reacts with. I'm not signing, to bless you. We've got a plus. Okay. Acetic acid. So I heard a C, and I'm already going to be like, no. Acid means H. So we put an H in front and an AQ in back. Anytime you see acid, you got to drop that in. The next part is dealing with the rest of what all of that means. That's a little bit harder to nail down. Why is that one a harder one to nail down?
You gotta memorize it.
That is a complex ion that you must memorize. Okay? Because I do not see the word hydro in front of this, I know this to be a ternary acid, which means I'm looking at a complex ion, which means this species right here is my acid, is my root with the ick. Ick means I ate too much, so I got sick. And I get acetate. Right? What is the acetate ion? C2H3O2. How do you know that? You have to memorize it. There isn't another answer. Okay, and for those of you going, man, can't believe I got to memorize. What is C?
Carbon.
Then shut your mouth. You already knew that answer. You had to memorize that. You got to do it for acetate too. Okay? More stuff. Deal with it. Okay? Is that formula correct?
No.
How do we know? Charge on hydrogen. This is why it gets tricky. I apologize. +1. Charge on acetate. -1. How do we know acetate's a -1? Memorize. Okay? If you didn't memorize it, you can't answer the question. This is why you've got to memorize it. Remember how I told you sodium? You needed to know the charge on sodium is? +1, because you memorized it. Guess what acetate is? Acetate's another element, as far as you're concerned. Except the symbol for acetate is C2H3O2. That whole thing. Yeah, it's a mouthful. Deal with it. Okay? You also have to memorize its charge is a -1. What's that?
Its whole charges.
The whole charge of acetate, C2H3O2, is a -1. Okay? To produce. Kind of sounded like a dick. I apologize. Sort of. I mean it in the nicest of ways. To produce means? Arrow. Equals isn't a bad idea. If this was a math equation, that'd be fantastic. In chemistry, we use an arrow. Aqueous sodium acetate. Batman. Somebody got it. At least one. That's all that matters. Acetate. You don't have to get it. It's okay. Sodium. What charge? +1. Acetate. -1. Is that formula correct? Yes, it balances out. I need the AQ because it says aqueous and there we go, a plus. Gesundheit. Hydrogen gas. H and gas. Hydrogen's an interesting one, which is why I'm actually using this example. Hydrogen is not by itself. It must be written H2. What we've now just worked through and done is two things. Number one, we started chapter 7. Yay! Chemical reactions. We've also reviewed chapter 6, nomenclature. Right? Both of those chapters show up on the test in systems like this. You have to be able to acknowledge what it means to write out a chemical reaction. You also have to know what all of those pieces are. Okay? So, we're not going to stress about balancing quite yet. How the hell did we know that was H2? Hydrogen needs 2 because science. Hydrogen is a diatomic molecule. This means when hydrogen is by itself, it must get written as H2. Okay? When can I write just H? When it says hydrogen atom, then it's just one H. Okay? Otherwise, if it says hydrogen, we're meaning 2. It has to be written as H2. It's diatomic. There are certain elements on our periodic table that are always diatomic when they're by themselves. We have hydrogen, nitrogen, oxygen, sorry. Did I just read off the slide? Screwed that up. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's a variety of ways to memorize this. This one I've got a little bit more sympathy for on memorization just because, right? We do need to memorize this. These are 7 to memorize. Right? So if we look at our kind of table here, let's work through a couple options. What does that look like? It kind of looks like a 7, right? If you don't think it looks like a 7, hold your tongue and just wait. We'll use a different one. For those of you that think that looks like a 7, how many elements did I circle? 6. It's supposed to be 7. There's the 7th. Ta-da! Tells you. Okay? Those of you that like colder climates might know what else this looks like. What the hell is that? That was down here, you could call it Cuba. Colder climates? A hockey stick? It's a hockey stick with a puck. And you could memorize it that way. For whatever reason, neither of those have actually stuck in my head all the way back to high school. Have no fear of ice cold beer. Have begins with
H.
hydrogen. No fear. Okay? So every time it comes to a diatomic element, you'll see me, and I usually mumble a lot of stuff under my breath. Okay? Have no fear of ice cold beer is usually something I'll just kind of crank out every so often just to make sure I remember those pieces. Okay? So you've got a variety of ways that you can memorize your diatomic elements. You do need to know them. Anytime they show up by themselves, you have to specify them as the 2 elements. Okay? I know you can hate me later. Mathematics simplifications. If I asked you to write that right now, you get super irritated at me because we got like 30 seconds left in class and your hand would get tired, right? Yeah. How could we simplify that? 4 to the 6th power. Cool. We're taking advantage of exponents. Those exponents simplify our calculations. That's why we use them. Okay? Your calculator can do this for you. Don't screw it up. If you don't know how to use your calculator, that's okay. Talk with me so we can get that figured out. You should not be learning how to use a calculator on the test. Okay? And everybody laughs. It happens every semester. Okay? So make sure you know how to use those. These ultimately show up really commonly in terms like squared and cubed. What is squared?
2.
How do you calculate the volume of a square? Volume, area? Length times width. Meaning? two things.
Yep.
Squared, cubed, length, width, height, three things. Okay, so you could see those terms pop up. I will stop, I promise. I won't continue on. We'll go ahead and end.